So AC922, we have multiple memory pools. Even if you have unified addressing, the physical memory is still distributed. Each GPU has its own HBM memory, 16 gigabyte in this case. So it's either 4 or 6 pools of HBM memory. CPU has, depend on the system, Summit has 512 gigabyte, Sierra 256 gigabytes, split even between the two sockets. So again, there is some distribution of the memory. What I don't show here, I don't mention, is that there is additional memory pool, mostly used for checkpointing, but actually can also be used as extended memory. It's 1.6 terabyte of NVMe. We are not going to talk about this, but it's another complication for those who really want to use all 3 levels of memory. And overall, there are about 1 million of threads that can run concurrently on a AC922. I will show you how did I get this number. But the point is that you have a number of challenges. One is managing the data, managing the memory. And we heard several times during talks today that it's really important to move the data to the right compute device at the right time to get the performance. And you need to manage the execution policy. Who is computing, CPU or GPU, which CPU, which core, how many cores. And you really need to take care of the parallelism, because there is a lot of parallelism at different levels. Just think about 2 sockets. In each socket, you have 2 or 3 GPUs. On each GPU, you have number of SMs, number of blocks, number of threads. On the CPU, you have cores. There are a lot of parallelisms that can be expressed as nested parallelism, flat parallelism. And depending how you take care of this, you get either good or bad performance. So when you think about data management and expressing parallelism, you also want to have your code that you develop for this system to be able to run on different systems, because this is what most customers do. Right? They don't care just about AC922. They also run on Intel system, on system with AMD, CPUs, GPUs, and so on. So you really want to design portable and performance portable codes, not just code tailored for a particular system. So we'll talk about this. The factors that help us quite a lot in design portable and performance portable codes are basically these 2 factors. One is unified addressing, and the second factor is the compiler directive. And this will be, most of my talk will be around the compiler directive, so OpenMP, that we use to program CPUs and GPUs. And I will show a number of examples, actually pieces of codes, that will describe how we manage memory and data, nested data structures, nested parallelism. Some examples from applications that we worked on for Summit and Sierra computers, and so on. And please do ask me questions whenever you have them. So parallelism, 2 Power 9 processors, 22 cores for users. Each core has 4 hardware threads, so you can compute how many threads are there in total. A Volta 100 GPUs, other 4, 6 GPUs, 80 SMs in each, 2048 threads per SM. So here you see how capable these compute devices are. So if you calculate the total number of threads, you arrive to about 1 million of threads that you want to use on the system to squeeze every single flop and every single gigabyte per second of bandwidth from the system. So your investment actually pays off. Memories. This is the view of memory that I have as a developer, application developer. So we have 2 sockets. We have this weak link between the sockets. In one of the talks this morning, it was mentioned that if you use the GPU from a different socket, your memcopy or CUDA memcopy memory bandwidth is not as what you would expect from NVLink. Yes, of course, because you go over the bus. It doesn't give you a lot of bandwidth. It's basically designed to move some operating system traffic over the bus and some communication when you go from the node to another node. So most of the connectivity between the memories happening inside each socket. So all 3 GPUs or 2 GPUs, as in case of Sierra computer, they are interconnected. So in this configuration, for example, we have total of 6 bricks for NVLink on the CPU side. So we split those between 3 or 2 GPUs, so either 3 bricks, and this is how you get 75 gigabyte per second unidirectional memory bandwidth, so bidirectional is 150 per GPU. Or on a machine with 3 GPUs, you'll have 2 bricks per GPU, so it will be 50 gigabyte per second in each direction per GPU. Okay. So when you design your application, you also need to take care about moving data. So you want to move it into the right place, in the right time, and as effectively as you can. There are a number of options to program this machine. So obviously for CPU, we can use GNU compiler, PGI compiler, Excel compiler, Clang compiler. For CPU, we have a number of options as well. We can use CUDA, right, coming from NVIDIA. We have some support for CUDA, also in Excel Fortran. We can use OpenACC, supported by PGI compiler. And we can use OpenMP. So using OpenMP for GPUs is kind of new thing. It's here for about maybe 3 years, starting from OpenMP 4.0 standard. Nowadays, we have OpenMP 4.5 standard. It advanced quite a lot. And OpenMP 5.0 standard is something that's coming soon. Right? Actually, a lot of people who are in this OpenMP standard committee work for IBM and work for National Labs, so a lot of experience that we got from working on the applications ended up in proposing new standards for the OpenMP. So I will talk about the OpenMP part. So why use OpenMP? Okay, so let's take this example. Like we have a very simple for loop, a DAXP application. This is sequential implementation. Just, nothing sophisticated, nothing fancy here, just for loop, y equal a times x plus y. And I can take this loop and incrementally improve the performance or speed of calculation by first creating threads on the CPU. So now I can use multiple cores and maybe multiple threads per core to run this loop in parallel. Next step, I can create nested parallelism using teams and parallel for, and still run it on the CPU. And next step, I can offload the computation to the GPU. So you see I increase the number of compiler directives here. And I will explain a little bit about almost all of them, what they exactly do. And then incrementally, I move my the execution of this loop from the CPU to the GPU. And if I switch, for example, inside this if target 1, if I switch 1 to 0, I will compute on the CPU. So the runtime actually can switch the execution from the CPU to the GPU depending maybe on the size of the problem that I'm going to solve. So if I need to add just 2 doubles, I'm not going to launch a kernel on the GPU. If I'm running dgem, for example, I better go to the GPU and so on. So OpenMP gives a lot of flexibility and it hides a lot of complexity from the user in order to offload some calculation from the CPU to the GPU. For example, in this one line of directives, what we do, we allocate memory on the CPU, on the GPU. We move data to the GPU, so at least 2 API calls, CUDA malloc and CUDA memcopy. We launch a kernel on the GPU. We express parallelism for the GPU, how many CUDA blocks, how many threads per block to use. And at the end, we also move data back from the GPU to the CPU and delete the memory allocated on the GPU. So it's a lot of operations that were expressed in a single line of directives. Now, in terms of performance, do we achieve good performance using directives as we would achieve typically using CUDA and working somewhat harder on the applications? In general, the answer is yes. And here, for example, I show results that were obtained on Minsky system, so it's Power 8 plus 4 Pascal GPUs. You see this factor of 12 in terms of the speed up. So this is more or less the factor that we expect to get for memory bandwidth limited applications. Right? So if we compare the bandwidth of 2 power 8 CPUs with bandwidth of 4 Pascal GPUs, we get about factor of 12. So OpenMP 4.5. OpenMP 4.5 can actually take care of a lot of challenges that we face when we program. So memory management, definition of execution space, managing data, nested power region, coarse-grained parallelism, fine-grained parallelism, inter-node communication. For example, if you need to move the data between the CPU and the GPU or different GPUs, it doesn't take care of inter-node communication. So for this, we typically use MPI or message passing interface. So OpenMP is out of the question there. Right, so I mentioned several times managing memory and managing data. And in my view, this is not the same thing, right? So why it's not the same thing? Because managing memory, for me at least, it means we need to allocate or deallocate memory. At this step, we don't care what data sits in these memory regions. We may use memory pools, so we can pre-allocate memory and then place different data into these memory pools. We can use unified addressing, and in this case, we'll have just single pointer that will point to some memory buffer that can reside on other CPU or on a GPU and be visible from both sides. And we can also provide some hints that may prevent some page migration, for example, from one NUMA domain to another, or from one CPU to a GPU, or from one GPU to another GPU. Now, managing data, so once we have memory, for example, we can place different data into this memory, right? So at one stage of the code, I can place some variables. Another stage of the code, I will just reuse this memory, place another thing, right? When we replicate the data on the CPU, on the GPU, which we often do with OpenMP 4, we need to synchronize data. For example, we start with all the data on the CPU side, and then we replicate on the GPU. We replicate data structure, we can put it on the GPU, and then we need to bring data back. Right? So sometimes it's easy. Sometimes when you have nested parallelism, synchronizing variables in like 5, 6 levels of nested data structure is quite complicated. So in this case, we really want to manage data because we need to synchronize between variables, nothing to do with managing memory here. Random switching between host and device. So in this case, host is the CPU and device is the GPU. For example, there's an application called AMG, Algebraic Multigrid. So the way it works, it solves very large problem, then reduce the problem size and continue solving smaller problem, and then reduce problem size, continue solving even smaller problem. It's called a V-cycle, when you go from very high resolution to low resolution, and then you come back to very high resolution. So what happens there is, when the resolution is very high, problem size very large, it's worth using a GPU. When the resolution is very low, it can be down to 1 point from a few millions of points, or maybe billions of points. Then you don't want to launch kernels on the GPU because there is not enough work. So at some point, you want to switch from computation on the CPU and the GPU. So if you replicate your data on both devices, you need to make a decision when you switch, and also you need to update the state of your solution on either CPU and the GPU. So this is something that you need really to manage. If we're using unified addressing, it's not a problem. The hardware or the system software will do it for you. It will move a page, or it will just compute using different device on the memory, which can actually reside on either side of NVLink. Well, using concurrent execution, for example, by host and device, if you have memory replication, for example, on the host, you want to update even numbers in the array, and on device, you want to update odd numbers in the arrays. Just as a wild example, how do you synchronize the data later on, right? You want to make sure that you put everything into the same array and everything has the same state. So this is quite a challenge. So in general, we have two options with OpenMP 4.5. One option is memory data management using OpenMP directives that can allocate memory, move data from CPU to the GPU, or from one GPU to another GPU. We have memory data management using unified addressing. It's typically much easier than the first case. Sometimes there are performance penalties. And we can actually also mix these two, probably the most efficient way and most productive way to write the applications. And I will show some examples. All right, so we continue the topic of managing memory and data. As I mentioned, in OpenMP, we can use directives. So those are map, enter data, release, delete. I will show a few of the examples. We can use OpenMP API calls. For example, OMP target alloc, which is basically a wrapper around CUDA malloc. Okay. OMP target memcopy, which is basically a wrapper over CUDA memcopy, so on. And we can obviously mix and match between directives and APIs present in OpenMP. So here, for example, I show a few clauses, a few directives. So for example, the two directives means I want to replicate data and I want to move it from either CPU to the GPU. So two directives, what it may do, it may allocate a new memory on the GPU, for example, if I move from the CPU to the GPU, and move the data to that memory, okay? And if it detects that the memory was already allocated, because we have pairing of two pointers, so if we, for example, get a pointer, point to the CPU memory, and that pointer doesn't have a pair pointing to the GPU memory, OpenMP runtime will figure out that, oh, now I need to allocate a new memory, I need to pair pointers, and those will point to some two structures, data structures, that I will maybe synchronize later on. So two helps you to allocate memory and move data. From does similar thing, but in the opposite direction. Data goes from the GPU to the CPU. To from, data goes both ways. Alloc means you only allocate memory and you may use it later on. Not every time you need to move data, it's actually expensive. Release means it may delete the buffer or it may skip deleting the buffer, just decrement what's called the reference counter. And I'm not going to dive too deep into this because it's another 30 minutes talk. Delete means just delete the memory buffer. So pretty much all of the calls are wrappers around CUDA APIs for CUDA memcopy, CUDA malloc, CUDA free, right? But they quite hide a complexity of programming from the user, and you can express a number of steps that you want to make in your application by using just few words, few clauses to the OpenMP. Okay, so here we have one example. So it's a very simple loop. It does sine of x times cosine of x. I just made it up. A lot of flops required here. And here I show how we can offload the execution from the CPU to the GPU. So first note the pragma OMP target directives. It means that now we are going to use target. The target can be actually device or host. If I don't specify anything in addition, so by default target is the device. In this case, is the GPU. Teams distribute means create some number of CUDA blocks. Okay, there is a default parameters. Excel compiler, for example, has some smarts in it, so we will try to figure out what will be the best number of CUDA blocks to request. And parallel for means in each block I want to use threads. So this is basically the size of each CUDA block, how many threads per block we are going to use. And again, there are default parameters. We can specify all these parameters also explicitly. And there are some smarts in the compilers that can try to figure out how many threads per block will be the most effective for this particular kernel. And then we have the map directive. So you see we take X, which resides first in the CPU memory. So the X points to the CPU memory. And we say 2. And what OpenMP runtime will do, it will see, OK, is this CPU pointer paired already with the GPU pointer? No. If no, then it will allocate memory for X on the GPU and copy the data from the CPU buffer here. I show it in sort of blue color to the buffer on the GPU. So basically, it will replicate the data on the GPU. And map from will check if Y has a pair, or if there is another pointer that points to the data on to the memory on the GPU. If yes, it will do nothing, and if no, it will allocate memory for Y, and at the end of this execution, it will also copy the data back to the GPU. It's a very simple model to offload execution from CPU to the GPU. We can use this joint set of pragmas. For example, at the beginning of our execution, we can map the data, allocate memory, move data that we need to the GPU, and release it or delete it at the end of the execution. And in between, we can have numerous number of kernels, functions that will reuse the already mapped data. So we don't have to put all the instructions at every pragma OMP target directives. And by doing that, we also minimize the impact on performance due to allocated memory, moving data, and moving everything back.
So I have a question.
Sure.
What happens? How do you control which devices this is going to?
So, yes, it does matter. First can be CPU or the GPU. So in OpenMP, there is.
If you have several GPUs.
Right. So how do you control which GPU will be used, right? So for example, on AC922, we can see, or each process can see up to 6 GPUs, right? So first you can make only one GPU visible, or 1 or 2 or 3, or up to 6, visible to each process. So you can make one, and then there is the only one. And second, there is a OpenMP API called OMP set default device. It's somewhat equivalent, but not exactly equivalent to CUDA set device. And you can choose the GPUs that you're going to use, and you can switch later on to a different GPU. We'll have an example where we will use multiple threads running on different GPUs. So you can launch tasks on different GPUs. Just need to be careful if you allocated memory on GPU 0, don't try to use that pointer for GPU 1. Right, so as I mentioned before, we can enter data at the beginning of the, some scope, right? Can be at the beginning of the application and exit at the end of the application or at some scope. And in between, we can have a lot of kernels that we launch on the GPU, and in this case, we don't have to specify all the map directives because the runtime that we have will detect if pointer X has a pair, CPU and GPU, and pointer Y has a pair on the CPU and the GPU. If it doesn't, in this case, your code will collapse, and you will see some error. If it does, it will work properly. Now, there is function A, and what I want to show that inside this function A, which can be called from anywhere in this code, and I don't know if it's going to be called from the region where I already entered the data or mapped the data from the CPU to the GPU or not. So in this case, it's called from within the region where X and Y are already mapped, or have a replica on the GPU. So in this case, what will happen, the map directives will be simply ignored. It will find that there is already a pointer pointing to the GPU memory. It will assume the data is synchronized already, so there will be no copy. And we'll just launch a kernel and execute it without any copy to or from of data. But if I call this function from the region, let's say I place it before the first pragma OMP target, enter, then what will happen, the OpenMP runtime, when it meets map 2, will check if pointer to the CPU memory X has a pair on the GPU. If not, it will allocate memory and move data to the GPU and so on. Here I've shown an example where you can actually use OpenMP for managing data and memory. And you can call functions highly optimized for a particular device. For example, this function is for QSparse, performance sparse matrix vector multiply. You can see I map the data using OpenMP directives, and then I provide another directive that within this scope, instead of using the CPU pointer, I want you to use the GPU pointer. So it will pass the paired GPU pointer to QSparse, and QSparse will basically compute what it needs to compute, and then it will exit, okay? So it's part of sort of cooperation between OpenMP and coding with CUDA. Deeply nested data structure. So deeply nested data structure can be quite a pain. For example, here I show a data structure from a code called Quicksilver. It is a Monte Carlo code used by National Labs. And here we see very unstructured data. So there are objects that have pointers to other objects. QS vector, it's kind of STD vector, something similar. So it has some size and pointer and a few other attributes there. So we have vectors and vectors within vectors, within vectors, within vectors. Typically, we have about 5, 6 levels of data nesting. So when we have that complexity in the code, using mapping for each of them becomes quite complicated. And there are some solutions, and I will go over these solutions. And this situation actually present in many of the real HPC applications where not everything looks like simple Duxby loop or something like this. So I will start with a very simple example where I have a structure which has a pointer, y, and it contains a size, right? So number of elements, and very simple constructor that gets pointer y and assigns to the a.y and get the size. So on line, for example, 8, I create a memory on the CPU. Allocate memory on the CPU, and on row A, I create an object of this structure A, and I provide a pointer to the CPU memory to this object, and also the size, the number of elements. Now I want to use this object on the GPU, right? So I need to replicate the data on the GPU. Say, okay, I will map A is a pointer, so just one value, to the GPU. I will map Y to the GPU, and I will try now to use Y, or A pointer to Y on the GPU, and my code will collapse. And the reason why my code is collapsed is when I do map 2 of A, I allocate memory on the GPU, and I perform bitwise copy from the CPU to the GPU memory. So if I do bitwise copy, it will copy the size, fine, but it also will copy the value inside the Y, and the value inside Y will basically point to the CPU memory. And if GPU cannot read the CPU memory, it will just fail, right? So, so there are different ways to deal with this. For example, we can map A, and then separately we can map A pointer Y, right? So in this case, everything will work fine. Or we can assign the value of pointer Y pointing to the GPU memory in some different ways, right? But if you imagine that we have 6 or 7 levels of nesting, then going through all these data structures and trying to assign the right pointers to the right structures and right pointers within the structures, it's very painful. And I think if you have the reference, and for example, one structure just assign the pointer which will be identical to the pointer in another structure, it quickly becomes very messy. And that doesn't mean that you cannot offload the code and your code will never run on the GPU. It means that you just need to use alternative techniques to port your code from the CPU to the GPU. And that problem is exactly the same if you program with OpenMP or OpenACC or with CUDA. So to alleviate this issue, right, to solve this problem of working with nested structures, something very deeply nested structures, we can use either CUDA managed memory, or we can use ATS. So in one sentence, we can use global addressing. Okay? And I will show a couple of examples here. So this piece of code is taken from, well, it can be taken from different applications, but in this particular case, it's from Lulesh. So we deal here with std vector. And with std vector, we do not have control on the pointer that points actually to the data, because this pointer is protected within the class. So we can have API that would allocate memory to this pointer, but we cannot change the value of this pointer, so now it will point to the GPU memory, right? So in order to be able to use std vectors on the CPU and the GPU in particular code, what we do is specialize the memory allocator. So it's a very simple trick that we do, and it actually saved us a lot in many different codes with nested structures. So instead of calling malloc, we'll call CUDA malloc managed. And this will give us a pointer which is valid on the CPU and on the GPU. And moreover, we don't need to replicate the data on the CPU and the GPU. The data and the memory and the data with the memory will move on demand when we touch corresponding page or cache line on either of the devices. Right, so in this case, the modification was really simple, just few lines of the code. We use if-def because this was the most portable way to make the minimum amount of changes in the code and have this code ready for different for computation on different hardware. Today we can use ATS, which is not exactly the same as a CUDA managed memory. It has some advantages and some disadvantages. So ATS stands, as was said in the previous talk, for address translation services. We basically can have malloc, right, on a AC922. And memory allocated with malloc is visible today for the GPUs and for the CPUs. Right? This memory wouldn't page today by the first touch or whatever touch. It will always stay in the CPU. And this is something that we're still working on with a Linux community and with NVIDIA, because the end goal is that memory allocated with malloc will be paged to the device that needs this memory, just as in normal NUMA system. But we can prefetch this memory, so we can explicitly prefetch and move the pages, for example, from the CPU to the GPU, or to the different GPU, or back from the GPU to the CPU. Okay? So we can modify or specialize the memory allocator for this std vector using, for example, ATS, not necessarily CUDA malloc managed. Now, one difference between ATS and CUDA managed memory is that with CUDA managed memory, only memory allocated dynamically can be seen by the GPU and the CPU. With ATS, all variables, global variables, everything that is on the CPU stack and everything that was allocated dynamically can be seen by both devices. With CUDA managed memory, if you try to push more than 16 gigabytes of data into the GPU, what will happen? Some memory will be swapped back to the CPU automatically. There is a performance penalty, but the code will not crash, it will run. And it might be handy in some application. We take this performance hit, but everything is managed automatically. With ATS, today, the memory will not be swapped. So you get to 16 gigabyte, and if you try to push one more byte into the GPU, your code will crash. So it's subject for future improvement. But today, this is how it works. Yes?
How big of a performance difference is there?
I have a slide. Good question. Yeah, we're always concerned about performance. So whatever we do, we always check the performance. Right? Having functionality is great. Having performance is even better. Yeah. So I will address this question. Okay. So I'll talk a bit more about ATS, the address translation services. So when OpenMP 4.0 became available, it was not obvious for OpenMP committee that OpenMP at some point will have to support also unified addressing. The model for OpenMP was, well, you start with all the data on the CPU, and you replicate on the GPU, and when need, you synchronize data, meaning you copy something from the GPU to the CPU, update some variable, or the other way around. It has been proven impractical for very complex applications, and the standard changed. OpenMP 5.0, for example, will allow users to prescribe how data can be synchronized with nested parallelism, how you map nested structures, and it also allows to use a unified addressing. Okay, so for example, here we have OMP set default device. There was a question about how we choose the device. So here an example. And here we have perfect valid OpenMP 4.5 code where we create a target region, we map the data that we need, create memory, and move the data back from the GPU to the CPU, and provide parallelism that we'll employ in the GPU kernel. And we can take this code and modify it, assuming that ATS is working, and we can say, well, data is actually device pointer, so it means it's valid device pointer. You don't need to map anything. You don't need to allocate new memory. You don't need to copy any data from the CPU, the GPU. Just take this pointer and run with this. So data was allocated on the CPU side. Currently, there is no page fault, or there is no implicit page fault. And what will happen, the GPU will run this kernel, but it will read or write data over NVLink. Just very similar to zero copy functionality when you allocate data with CUDA host alloc, and then you can access this data from the GPU. The main difference between new and ATS and CUDA host alloc is that new will take probably less than millisecond or so, and CUDA host alloc will take about 300, 400 microseconds. So it's a big difference in time that's spent on memory allocation. So not how long this string is, string of OpenMP directives. It's much longer than this loop in this example, right? So pragma OMP target team distributed parallel 4 is device pointer, and actually can be much longer than that. If target, if something else, map to, from, and so on. And we would like to reduce actually this burden and have this even more compact. So the current OpenMP runtime that IBM provides for OpenMP allows to export some environmental variables that will tell OpenMP runtime whatever pointer we get, if it's not mapped, assume that it's a valid device pointer. So developers don't have to write this is device pointer. OpenMP will assume that it's a valid device pointer. Okay? It will not even check. It will check only if the data was mapped to the GPU through a map directive. And if not, it will just pass the pointer to the GPU kernel and you'll run with that. You can also mix. You can mix explicit directives and assume that some pointers are valid device pointers. For example, what will happen in this example, I have an array of 2 doubles. So it's really small array. Once I touch it on the GPU, it becomes, actually it sits in the registers, not in the cache. It sits in the registers. So allocating memory for 2 doubles and deallocating and moving data from CPU to GPU will take way more time than about 400 nanosecond latency that will be needed just to grab these 2 variables. So in this case, I will use a data array, which will sit in the CPU memory. Compiler will understand that, and OpenMP runtime will understand that it's a valid device pointer because we use ATS and we also export some environmental variables. And on top of this, I'll map data too, because it's large array, maybe want to keep it on the GPU for later use, I will map it explicitly. So this already works, and it's actually very handy for many codes. So I showed examples for C++ applications. We have similar for Fortran applications. So C++ typically is the language where we improvise first and try to figure out how things work, and then we move improvements into the Fortran language. So here I show an example where first time when you run this little code where memory is allocated on the CPU, right, and ATS is on, what will happen is that in Fortran, the runtime will detect that pointer has not been mapped, so it will map the data array explicitly. It will actually allocate the memory for it, and then it perform CUDA mem copy. You can see this NVProf profile, so you see what happens there. There's a memory allocation, which we don't see here, but we do see CUDA mem copy. Then we see the kernel that runs at 1.6 microseconds, and then there is a mem copy from the device to host. And now we are going to run exactly the same executable. The only difference is that we export this environmental variable that OpenMP runtime will detect, and it will act accordingly. So now it runs exactly the same code. What happens here is that we don't see any mem copies, because now it implicitly understood that every pointer that we pass to the GPU kernel is the valid device pointer, and we don't need to map data. We don't need to allocate new memory. We don't need to copy data. And you can also see that the kernel runtime actually increased by a factor of 6. Oh, yeah, about a factor of 6. So why is it so? This is so because now we run the kernel on the GPU, but it reads the data from the CPU memory over NVLink. So this is a small problem, but if it would be bigger problem, right, it's only 20 doubles. Bigger problem, what you will see in memory bandwidth limited application, the speed will be proportional to memory bandwidth. Performance, there was a question about performance. So this is one of the Coral 1 benchmark that was used for acceptance of Summit and Sierra. It's called LULESH. It's what's called the base version. The base version, the definition of the base version is that we can use only compiler directives and minimal code changes in order to port application from CPU-only application to application that can run on heterogeneous system. We are not allowed to do some deeper changes. For example, we are not allowed to change data layouts. We are not allowed to change, merge, or split kernels, and so on. So really minimal, maybe like cosmetic changes in the code with directives in order to port this application. So LULESH using STD vectors, and what was done, we specialized the memory allocator for STD vectors, either using ATS, as I showed before, or using CUDA managed memory. And we decorated a parallel region, pragma-OMP parallel 4, became pragma-OMP target team distributed parallel 4, with maybe a few directives of mapping. And this was pretty much it for this code. And what I compare here, when we use 1 MPA run per GPU, so only one process per GPU, it's exactly the same code, just the memory allocation is different. We get FOM is figure of merit, so it's like a speed, right? The higher, the better. We get comparable performance, but a little bit better performance with ATS. So what happens with ATS, we allocate memory on the CPU, and then we push it to the GPU. We prefetch it, so all the pages, everything located on the GPU. Now, if CPU wants to use that memory, want to address this memory and use data, what happens, it will address through the NVLink. So it will not go from the CPU to the GPU, it will go from the GPU to CPU, it will go from the CPU to the GPU, right? So kind of reverse zero copy operation. And it will cache the data in the CPU L3 cache. Okay, so there will be no page migration, implicit page migration during the execution time. Here we run the same code, and we put 2 processes per GPU using MPS. And we have slightly better performance, about 10% better performance. And also with ATS, we get better execution time. So did answer? Yes, it will be pretty much as writing the code on the CPU, because it will go with the NVLink bandwidth, maybe a little bit better if it's a flop limited application like DGEM, for example. You can read from the CPU. You still will benefit from the GPU, but yes. Nested parallelism. So in this example, what I'm doing here, I say, well, okay, I have two GPUs in my system, in my socket, and I have a lot of cores. So, and I have some problem to solve. So I will just take part of the problem or some kernel and offload it to GPU 0, another kernel or another part of the problem I will offload to GPU 1, and the rest I will solve on the CPU using all the cores. So I'm trying to maximize the use of all the compute resources in the system. For some applications it makes sense, for some applications it doesn't, but the capability is there. So what I do here, I just create pragma-NP parallel region on the CPU. So now I have a number of threads, in this case 3 threads. If it's thread number 0, I will offload work to device 0. If it's thread number 1, so this is more like a cartoon, it's not real code, I will show the code. I will offload a task to GPU 1, and otherwise I will create a nested parallel region, and I will use the rest of the CPU cores and threads in order to solve the remaining of the problem. So here's a little code. I'm sure if the slides will be available. Right, so for those who are interested, probably can just copy this and it's the entire code. So just compile it and run it pretty much. Right, so it shows how I create a region on the CPU, parallel region on the CPU, select the device that I want to use, launch the kernel, and another thread will select a different device, launch a different kernel, and the remaining threads will perform calculations on the CPU. I show another example also from Lulesh where we have nested parallelism. So we have a couple of threads, basically pragma-NP section, right? A couple of threads running on CPU, and each executing different tasks, right? So each thread launch a kernel on the GPU. So now 2 kernels can run in parallel because they go on from different threads. They will go also over different streams because OpenMP runtime, IBM's OpenMP runtime, will pick a different stream for every consecutive kernel or memcopy and so on. Here we have another example of nested parallelism. So again, we create 2 threads on the CPU. Each thread launches a kernel, basically calls a function. That function can be run on either CPU or the GPU. There is this little if target use device. So use device can be 0, then it will run on the CPU using more threads, the rest of the available threads, or it can run on the device if use device is equal 1, and basically we can get either remaining of the CPU threads solving these problems, or there are 2 kernels that will be launched on a device. Few words about asynchronous execution. So there was one example before where we saw that when GPU is computing, so this is the utilization of GPU, all these colorful boxes represent kernels running on the GPU, and you see these white spaces. White spaces means GPU is doing nothing, so it's kind of wasted investment. And we want to eliminate these white spaces. So now, why there are white spaces, why there are gaps in GPU performance, is because it takes some time to launch a kernel, it takes some time to perform memcopy, so kernels cannot go back to back, right? If everything is synchronous. Synchronous in this case means when CPU launches a kernel, it will do nothing until kernel is complete. So it's synchronous between the CPU and the GPU, right? OpenMP 4.5 and above allow to use asynchronous execution through the no wait and depend clauses. So it will, the depend clause will basically specify what is the dependency, right? I can have, for example, 500 kernels, and kernel number 37 will depend on a outcome of kernel number 2, so I can use the same variable for depend clause. So the kernel number 37 will start only after kernel number 2 will finish, right? So now with asynchronous execution, when first kernel is being launched, then CPU becomes available for the next task. And the next task for the CPU is to launch the next kernel. So it launched the next kernel. It goes to the GPU. It can run in parallel if there are enough resources on the GPU. If there are not enough resources, it will be queued and it will wait for its own turn. But the CPU will become available to launch the next kernel, launch the next memcopy. So it pipeline tasks. And as you can see, the number of white spaces, these gaps between the GPU kernels now narrowed to a minimal amount. And some kernels also run in parallel on the GPU. The performance impact is quite substantial in this case. It's about, I think, like 30% or so. GPU shared memory. Does it ring any bell? Do you need to explain what GPU shared memory is? So GPU shared memory is a region in L1 cache that can be explicitly managed by the application. So L1 cache sits very close to the compute devices. The latency to L1 cache is very low. The bandwidth to L1 cache is very high. And in some application, it makes sense to use explicitly as a scratchpad and place some data in the L1 cache instead of pulling it constantly from the main memory, HBM memory. So with CUDA, it's quite easy to allocate buffers in the L1 cache or in a shared memory, shared between the threads of the block. With OpenMP, there is no API, there is no way to explicitly allocate, but there are some smarts in the compilers that we put that may detect this static memory allocation, as you see in line 29, with known to the compiler, the compile time size of the buffers. And if the size of this buffer val is small enough compared to the size of the shared memory, it will allocate this buffer in the shared memory. And this will give us huge speed up. You can see that in this example, if we are using shared memory, we run this basically matrix transposition algorithm at about 900 gigabytes per second. So we maximize, it's actually a little bit less. We maximize the GPU bandwidth. And if we are not using shared memory, that memory allocation will take time because memory will be allocated in the HBM by each team or each CUDA block. And the data will go from the GPU main memory to the SMs and back at lower pace. So it will run at about 40 gigabytes per second. And I'm done.